radius of convergence. Let's think about a not too mysterious function.
Well, let's think about the function f of x equals 1 over 1 plus x squared.
I can write down a power series for this function around 0.
So I'll begin with the power series for 1 over 1 minus x. That's the sum, n goes from 0 to infinity, of x to the n. Now I'll replace x by negative x, and then I'll find that 1 over 1 plus x is the sum, n goes from 0 to infinity, of negative x to the n, which I could write as the sum, n goes from 0 to infinity, of negative 1 to the n times x to the n. And now, to get from 1 over 1 plus x to 1 over 1 plus x squared, I'll just replace x by x squared. So 1 over 1 plus x squared is the sum, n goes from 0 to infinity, of negative 1 to the n times x squared to the n, which I could also write as the sum, n goes from 0 to infinity, of negative 1 to the n times x
to the 2n power. What's the radius of convergence of that power series? I was being super sloppy when I wrote this out. I wrote 1 over 1 minus x equals this power series, but that's not true unless I include this statement. I should have written this down. If the absolute value of x is less than 1. And if that's true, then these are equal. The radius of convergence of this series for 1 over 1 plus x squared is also 1. And we can see that in the graph. Here I've graphed the function 1 over 1 plus x squared. And take a look at its Taylor series expansion around the point 0. Here's just the first term, which is the constant term. Here's through the quadratic term. Here's through the x to the 4th term, through the x to the 6th term, and so on. And you can see that it's doing an increasingly good job of approximating the function between minus 1 and 1. But over here, it's actually doing an increasingly bad job.
1 over 1 plus x squared looks like a really nice function. So if it's such a nice function, why isn't the Taylor series centered around 0 doing a better job of approximating the function far away?
Well, here I've graphed y equals sine of x. And honestly, I mean qualitatively at least, this isn't so different looking from the graph of 1 over 1 plus x squared. The graph of 1 over 1 plus x squared had kind of a big bump in the middle, and this thing's just got lots of bumps. And yet the Taylor series is just totally different experience. Let's start writing down the Taylor series around the origin. So here's the point around which I'm expanding. Here's just the constant term in red. Here's through the linear term. Here's through the cubic term, and I'm going to keep on going. And as I add more and more terms in my Taylor series expansion, I'm getting increasingly good approximations to sine of x everywhere.
Sine of x is equal to its Taylor series centered around 0 for all values of x. Whereas 1 over 1 plus x squared, its Taylor series around 0 is only equal to 1 over 1 plus x squared if x is less than 1.
And we know other examples like that. Like this. This is the graph y equals 1 over 1 minus x. And I can start writing down the Taylor series around this point. Here's the constant term, the linear term, and take more and more terms. And yeah, I mean the radius of convergence here is 1.
But maybe that isn't so surprising. I mean, 1 over 1 minus x has a bad point at 1, right? I don't want to plug in x equals 1 because then I'll be dividing by 0. This function's not defined at 1. So if I start a Taylor series around 0 and I imagine how big do I really expect that radius of convergence to be, well, you know, an interval of radius 1 centered around 0 bumps into the problem point. So maybe I don't really expect the radius of convergence to be more than 1 at 0.
So maybe 1 over 1 minus x has a problem when x equals 1, but 1 over 1 plus x squared doesn't have any problem at 1. It doesn't have any problem anywhere. This function is defined for all x. So if 1 over 1 plus x squared looks just as nice as sine of x, why is the Taylor series for this function centered around 0 so much worse than the Taylor series for sine of x centered around 0? Taylor series for sine of x converges to sine of x everywhere, and the Taylor series for 1 over 1 plus x squared is only good in an interval of radius 1. Well, let's see what happens if we write down a Taylor series expansion for 1 over 1 plus x squared, but not centered around 0, but centered around some other point. Let's write down the Taylor series expansion centered around x equals 1. See what happens. So here we go. There's the constant term, there's the linear terms, and we keep on going. We add more and more terms to the Taylor series expansion centered around 1. And I mean, we're doing an increasingly good job, but not over the whole real line again, right? But at least the radius of convergence is bigger now. Well, how much bigger? The Taylor series for 1 over 1 plus x squared centered at 0 has radius 1. The Taylor series centered at 1 turns out to have radius the square root of 2. And we had this idea that maybe places where the function is undefined, these bad points where the function doesn't exist, maybe those are somehow to blame for the radius of convergence. And that's what happened in the case of 1 over 1 minus x. Right? The radius of convergence around x equals 0 was 1 because this function has this bad point at x equals 1. The function's not defined if I plug in x equals 1. Maybe I'm bumping into a bad point here too. Well, let's diagram the situation this way. Here's the real line. And around 0, I've got this, well, it's an interval, but I've drawn it as a circle. It's a circle of radius 1. So that's representing the radius of convergence of my Taylor series around the point 0 for the function 1 over 1 plus x squared. Now around the point 1, right, I've got a different radius of convergence. It's bigger, it's the square root of 2. So here is a circle of radius the square root of 2, and I'm placing it so that its center is at 1. And the idea here is to try to get a sense of whether or not maybe I'm bumping into a bad point. Is there some point on the real line which is distance 1 from 0 and distance the square root of 2 from 1? But there isn't such a point on the real line. Okay, but when I draw them as circles, the circles are touching at these 2 points. So where is that point? Well, those points are in the complex plane. That point there is I, and that point there is minus I. Right? Those are square roots of minus 1. Those are imaginary numbers. Well, what happens if I evaluate 1 over 1 plus x squared when x equals I or x equals minus I? So I squared is minus 1. So what's f of I? Well, f is 1 over 1 plus its input squared. So that would be 1 over 1 plus what's I squared? It's negative 1. 1 over 1 plus minus 1, that is not defined. That's divided by 0. So there is a bad point. There is a point where the function is undefined. It's just that the bad point for this function isn't a real point. It's an imaginary input. Right? If I evaluate this function at I or at minus I, it's undefined. And yet that bad point in the complex plane is messing up my radius of convergence even along the real line. We're beginning to get a glimpse of the important role that complex numbers play even in the theory of just real-valued Taylor series. Additional evidence comes, for example, by this equation, e to the ix equals cosine x plus I sine x. And again, I is a square root of minus 1. And you can interpret this really as a statement about power series. So here I've written down the Taylor series for e to the x, but with x replaced by ix. Here I've just written down cosine of x, and here I've written down sine x, but I've multiplied by I. And you can expand this out using the fact that I squares to minus 1 to get this equality. And you can do kind of fun things like substitute in, say, pi for x, and conclude that e to the I pi is cosine pi plus I sine pi. So cosine pi is minus 1, sine pi is 0, so e to the I pi is negative 1. Taylor series aren't just a jumping off point for calculus and for numerical approximations. Taylor series are also our first step into the theory of complex analysis. And that theory is more natural than it might seem at first. I mean, if the complex numbers are affecting the radius of convergence of my real power series, then they must be really there. I mean, they're not as imaginary as people might think. So Taylor series aren't just a jumping off point for calculus and for numerical approximations. Taylor series are also our first step into the theory of complex analysis. And that theory is more natural than it might seem at first. I mean, if the complex numbers are affecting the radius of convergence of my real power series, then they must be really there. I mean, they're not as imaginary as people might think.